We all see how amazing large language models are getting, and these agents built on them, things like LangChain or MetaGPT, well, they're doing some incredible stuff, planning, using tools, even working together. But, even with all that power, they still run into problems, especially with really complex searches or deep reasoning tasks. It often seems to come down to limits in planning or maybe getting the nuances right in question answering or even just calling an external tool correctly. So if these agents are so smart, where are the sticking points really? And how can we push them even further? Today we're doing a deep dive into some fascinating new research. It looks systematically at how giving these agents more, let's call it thinking time, or as the researchers say, test time compute scaling, can really boost how effective they are.
Right, and test time scaling here, it's not about more training. We're talking about putting more computational horsepower behind the model while it's actually doing its job during inference. The idea is you give it more resources as it works and performance improves. But just taking old methods like, say, best of n sampling, it gets tricky with these agents.
Why is that?
Well, because agents tackle problems in steps, right? Sequentially. So if you just generate n options at the start, errors can cascade down the line. It's not like a single question answer. Applying those traditional scaling methods directly is challenging. And this specific paper we're digging into, scaling test time compute for LLM agents, from the OPPO AI agent team, it's dated June 17th, 2025. It's really important because it's the first time someone systematically looked at how these scaling methods work specifically for language agents. They pinpoint strategies that actually make a difference.
Okay, so let's get into those strategies.
Yeah.
How do they try to give these agents more thinking power? They started with parallel sampling algorithms, right? For listeners maybe not super deep into agent design, what does that mean and what do they find?
Absolutely. So parallel sampling basically lets the agent explore multiple paths or potential answers at the same time. They adapted a few key algorithms. There's the classic best of n or BON, just try n ways in parallel for a step, pick the best. Then a variation, stepwise best of n, BON-wise, which does that try n ways at every single decision point. They also looked at beam search, expanding the most promising paths, and a more complex one called diverse verifier tree search, or DVTS.
Okay, so trying different ways to explore multiple options, how did that pan out?
Well, the big takeaway first. Using these parallel sampling methods significantly improves agent performance overall. That was clear. Interestingly, the straightforward BON actually gave the best overall gains. We're talking an 8-point jump over the baseline GPT 4.1.
8 points,
Yeah,
wow.
and it hit state of the art on level 1 and 2 tasks. Those are the ones that really depend on using tools correctly. The thinking is BON gives the agent more chances to try similar subtasks again and again, especially those tricky tool calls. It lets it kind of brute force its way to the right usage.
All right, just more shots on goal for those specific, often finicky tool interactions.
Exactly. Now, BON-wise, the step-by-step one was second best overall, but, and this is interesting, it actually performed best on the really hard level 3 problems.
Why the difference there?
Because for those super complex multi-step challenges, you really need to explore broadly at each decision point, like checking every possible turn in a maze. Bondwise gives the widest exploration in each node, which seems critical for deep planning.
Makes sense.
But notably, beam search and DVTS, they didn't show much improvement over the baseline. It seems their success really hinges on how good the verify model signals are, and maybe those signals just weren't accurate enough to guide the search effectively.
So it's definitely not one size fits all. Simple parallel attempts work well for tool use, but that deeper step-by-step exploration is needed for complex planning, a really key finding. Okay, but what if an agent starts down a path and it's the wrong one? Especially in a long chain of steps, can they backtrack or rethink? That leads us to the next area, sequential revision strategies. They looked at self-reflection, right? How did that work out?
Yes, self-reflection. The idea is the agent sort of pauses, summarizes where it is and what it's done to try and figure out the best next step, but the research found something crucial. It's really about when the agent reflects. That matters a lot.
How so?
Well, initially, just making the agent reflect at every step didn't show clear benefits. Actually, it sometimes even seemed to disrupt the flow a bit. The overall score with constant reflection was slightly lower than the baseline 55.15 versus 55.76. It's almost like interrupting the thought process too much was counterproductive.
Huh. So nonstop navel-gazing isn't the answer for AI either.
Apparently not. It might break that chain of reasoning. So they tested a smarter approach, threshold-driven reflection. Reflection only happened if a separate verify model scored the current step below a certain threshold, suggesting something might be wrong.
Ah, like an only reflect if you're struggling approach.
Precisely. And they tried different thresholds. Reflecting too often, like if the score dropped below 8 or 5, actually hurt the overall scores. Especially on those level 2 tasks, it seemed the interruptions were detrimental. But, and this is the key detail selective reflection, only triggering when the score was really low, below 2, indicating a likely significant error, that achieved the best result overall, 56.36. It outperformed everything else across all task levels.
That's fascinating. So it's not about constant self-critique, but strategic, infrequent checks when things seem genuinely off track. Keep the flow going unless there's a good reason to pause and rethink. Like a good manager, maybe. Step in when needed, but otherwise, trust the process. Okay, we've got parallel thinking and strategic course correction, but when you have all these parallel paths or revised attempts, how does the agent actually decide which one is right? How does it verify accuracy and merge results? Let's talk about verifiers and result merging methods.
Right, this is critical. How do you pick the winner from all those generated possibilities? The paper compared a few ways to do this. There was simple voting, most popular answer wins, then scoring each potential answer gets a confidence score, and finally something they call a list-wise approach.
List-wise, how's that different?
Instead of just scoring each option on its own, the list-wise method directly compares multiple candidates against each other. It ranks them relative to one another, and the results here were pretty definitive. The list-wise approach consistently did better, both for verifying steps along the way and for merging the final result.
Consistently better.
Yeah. For merging results, they tested this with Bond and Beam search. List-wise beat voting and scoring by a noticeable margin. Like with Bond, list-wise merging got a score of 63.03, while voting was only 56.8 and scoring was 59.39. Similar gap for Beam search. The paper points out that list-wise can pick out the correct answer even from a diverse set of candidates, which simple voting might miss if the right answer isn't the most common.
Okay, so direct comparison helps find the best, not just the most popular or individually high scoring.
Exactly. And it was the same for verification during the process, too. When used with methods like bond-wise or tree search, list-wise verification generally scored higher than just scoring individual paths. For bond-wise, list-wise verification hit 58.79 compared to 56.36 for scoring. It suggests that comparing trajectories directly gives you a more accurate assessment than just assigning isolated scores.
So that head-to-head comparison seems really powerful. It's not just, is this good, but is this better than the alternatives? That sounds like a really valuable insight for anyone building these kinds of agent frameworks. Does it cost more computationally, though?
Well, yes, comparing multiple candidates directly is likely more computationally intensive than just scoring one or voting. The paper doesn't dwell on the cost aspect, but it's an implicit trade-off. But the argument is that the gain in precision, especially for complex tasks where you might get very different potential solutions, makes that list-wise comparison worthwhile.
Right, the accuracy gain justifies the potential extra computation. Okay, so we have parallel exploration, smart reflection, and robust comparison for picking the best result. What about making sure the initial pool of ideas is broad enough? Especially for tricky question answering, maybe. Did they look at strategies for diversifying rollouts, making the exploration wider?
They did. The core idea is simple. A wider, more diverse set of initial attempts or rollouts increases the chance that the correct answer is in there somewhere. They looked at this in two main ways. First was just sampling width, basically letting the agent generate more initial attempts or candidate solutions for any given step. And, maybe unsurprisingly, they found that increasing this width led to significant performance boosts.
More tries equals better odds.
Pretty much. It lines up with what we see in general. LLM scaling more compute for more samples often helps. But the second way was, I think, even more interesting. Multi-agent collaboration.
Ooh, like a team of agents.
Sort of. They use different large language models as the rollout generators. So instead of just GPT 4.1 trying things, they had combinations like GPT 4.1 plus Claude 3.5 or Claude 3.7 or Gemini 2.5 PRO, all generating potential paths or answers for the same task.
And how did that work?
It worked very well. Finding number 4. Increasing diversified rollouts enhances agent performance. And crucially, combining different models consistently yielded better results than just using more samples from GPT 4.1 alone. For instance, they showed a 4-model combo reaching a pass at 4 score of 74.55. That means it got the right answer within 4 attempts almost 75% of the time. That actually beat the existing open source state-of-the-art on the benchmark they used.
That's really significant. It makes intuitive sense too, right? Different models likely have different strengths, different ways of reasoning, or maybe different knowledge blind spots.
Exactly. One might be better at logic, another at tool use. Another might have more diverse training data in a certain area. By combining them, you're maximizing the diversity of the exploration. You cover more ground, increasing the odds that one of them finds the optimal path or answer, especially for complex reasoning where there isn't just one obvious route.
So how did they combine the outputs? Was it just feeding everything into that list-wise comparison mechanism?
That seems to be the implication. The different models act as independent generators, creating a diverse pool of candidates. Then the verification and merging steps, like the listwise methods we discussed, are used to evaluate and select the best outcome from that combined pool. It's less about active coordination and more about leveraging inherent diversity.
Got it. Of course, running multiple big models simultaneously must have cost implications.
Oh, absolutely. It increases compute cost and likely latency. But again, it's a trade-off. For really tough problems where top performance is critical, the results suggest this multi-agent diversification strategy is a very powerful tool.
Okay, this has been incredibly insightful. Let's quickly recap the main takeaways from this OPPO AI agent team research. First, parallel sampling helps. A lot. Simple best of n is great overall, especially for tool use, while stepwise best of n shines on deeper, multi-step planning.
Right. Second, reflection needs to be strategic. Constant reflection can hurt. Selective reflection triggered by low scores works best. It's about when you reflect.
Third, for picking the best path or answer, that list-wise comparison method consistently outperforms simple voting or scoring. Direct comparison is key.
Mm-hmm. And fourth, diversity matters. Increasing rollouts, either by sampling more widely with one model or, even better, by combining different models, significantly boosts performance, leveraging their unique strengths.
So fundamentally, scaling compute resources intelligently at test time, giving these agents more processing power in specific ways while they're working, is a really potent way to enhance what they can do.
It really is. It shows a clear path forward for making these already powerful agents even better at tackling complex planning, reasoning, and tool use challenges.
So the next time you see an AI agent working through something complex for you, maybe automating a workflow, answering a tricky question, just pause and think about the potential complexity underneath. Is it exploring dozens of paths in parallel? Is it pausing to reflect only when truly necessary, or its potential answers being rigorously compared against each other? Or could there even be a whole committee of different AI minds collaborating behind the scenes to find that single best response for you? It definitely adds another layer to how we think about AI performance, doesn't it?